let's say, the sphere here. This color is kind of like, it gets to you after a while. Let me see. Oh, my blue pen is working. Okay. So sphere here. So if it's a conducting sphere, this kind of resembles the topic that we did in chapter 22 with Gauss's law. Gauss's law. So remember, we learned about the electric field inside of a conducting sphere is zero. All the charges push out on the outside. And everywhere inside the electrical field is zero. On the outside, the electrical field drops as 1 over r squared. So the graph looks like this. 0 with an open hole. And then here, it like this. And then here at the surface, it's kq over r squared. So that's the graph of the electrical field of a conducting sphere. So what would the graph of its voltage look like? Okay. So spheres are kind of easy, especially when you're outside. They have a spherical symmetry. So they're going to be the same function as a point charge, right? The one that's kind of tricky is when you go inside. So on the outside, we would expect them to just simply behave like a point charge. And it's going to be like this, kq over r. The kq over r behavior that we expect from a sphere, from a point charge outside of the point charge, right? But then what happens at the surface and what happens inside? To do that, what we can do is argue that the voltage difference between any 2 points, A and B, of the sphere inside, VB minus VA, is negative the integral of E dotted into dr. So it's like, in this instance, when you go inside the spheres and cylinders, it's easier to first use Gauss's law to calculate the electrical field inside spheres or cylinders, then work backwards by integrating them to get the voltage inside them. So in this case, the other opposite is true. Usually I've been telling you it's easier to get the voltage of rods or semicircles or stuff and then differentiate them, or rings, plates, right? But in this instance, when you go inside of spheres and cylinders, use the opposite technique. Use Gauss's law to derive the equation. We would derive a general equation for the E field as a function of R inside of the sphere, right? Or not a question, but just a statement here. And then once you do that, then you negative integrate it. Well, for a conducting sphere, the electrical field is zero. So what does that mean? If the electrical field is zero, that means everywhere inside of the conducting sphere, the voltage is the same. So the voltage here and here is the same, the center and here is the same. Well, if they're the same, what are they equal to? You see? Well, here's the argument I'm going to make. If this is the same as this, which is the same as this, which is the same as this, which is the same as right before I get to the surface, right? So that's this thing, KQ over R, right? So that means they all of the voltages must equal whatever the voltage is at the surface. That's the tricky thing, because most people think, oh, if the electrical field is zero here, the voltage must also be zero. No, it's opposite. The voltage here is constant, not that it's zero. So the voltage is constant. You see? So think about this graphically. this function is always negative derivative of this function. So if this is some function, let's say y of x, this is negative y prime of x. So always try to, once you come up with a graph of this, take the derivative of it, but then attach a negative. So if you take a derivative of a constant, what do you get? 0, right? So it should make sense. The constant should be 0. And if you take the derivative of a kq over r, you get negative kq over r squared. But then you attach the negative, then you get kq over r squared. Let's see. Kq over r squared. Negative y prime. So that means if you have a conducting sphere and the surface of that sphere is 10,000 volts, right? And you are inside of that sphere, are you safe? Right? And the answer is yes, because your head will be at 10,000 volts and your legs will be at 10,000 volts. You see, this is what's known as a Faraday cage. As long as you're inside of a charged sphere which is conducting, the electrical field there will be 0, and all points of the sphere will be at the same voltage. So it's not voltage that kills you. The whole thing could be at 10,000 volts. It's not voltage that kills you, but it's voltage difference that kills you. You see, if your head was at 10,000 volts and your legs was at 0 volts, oh man, you better run. Right? So it's, if there's a voltage difference between you, the sphere, Matthew, the sphere can be either a hollow sphere or it could be a purely conducting metal sphere where the charges are all pushed out to the outside. The net charges are all pushed to the outside. So this could be both. This would be true for hollow spheres. Good question. Hollow spheres. Let me get another pen. True for a hollow sphere. Or conducting sphere. So it could be like all solid. Of course, in that case, you wouldn't be able to get in. But if it's all solid, but if it's pure metal and it's good conducting, if there's any net charge, it pushes itself out to the outside. You see? So either one. You see, so a Faraday cage or Faraday shield is an enclosure used to block electromagnetic fields. A Faraday shield may be formed by a continuous covering of conducting material, or in the case of a Faraday cage, by a mesh of such materials. So it's kind of an enclosure, kind of you're trying to create like the hollow sphere concept. And then you see, if you get inside of it and she's touching that, but all her body's charged to the same voltage. As long as you're inside, oh wow, look at that. Can't believe that. I don't know if I would do that, man. Do you guys believe in physics that much to trust yourself? Look at that. So you see, he's charging the whole cage, right? But all the charge is on the outside, do you see? So he's trusting that whatever voltage that cage is, every part of his body will be at that same voltage. I guess he's right. you know, because he's not dead yet. Wow, that's really putting your knowledge to the test. Extra credit? Anyone willing to do that? I'm down. Wow, that's really, really extreme. Talk about extreme sports. But there's other uses of it other than these kind of things. Because when I was typing it, even other things came up like Faraday cage. Are Faraday cages illegal? Although electric jamming devices are illegal, a Faraday cage is not. Unlike jammers, Faraday cages don't proactively cause interference, although they do interfere with mobile reception. Does Faraday cage block Wi-Fi? Faraday, an English scientist, built what is now known as the Faraday cage, an enclosed space constructed of the conducting material that blocks electromagnetic waves from entering or exiting. Inside this cage, those Wi-Fi and cellular signals would be rendered totally useless. Oh, wow. Can you use aluminum foil as a Faraday cage? Typically, wrapping your Faraday cage in several layers of heavy aluminum foil will give you the needed skin depth to protect your electronics from high-frequency radiated fields like the kind generated by EMP. So you can kind of see that this could be used to do to shield your electronics from high electromagnetic waves. Can a microwave be used as a Faraday cage? A microwave oven utilizes a Faraday cage, which can be partly seen covering the transparent window to contain the electromagnetic energy within the oven and to shield the exterior from radiation. Oh, so a microwave already has the concept of the Faraday cage. It says, can be seen covering the transparent window to contain electromagnetic energy. So it must be enclosed with like a mesh type material, you know, like the one we saw. What is the best material for Faraday cage? The material that works best is aluminum, copper, or chicken wire for a chicken wire Faraday cage. A lot of contact between the metal components, so mesh design can work well. See, the meshes work well because there's a lot of contact between metal parts. Oh, he keeps going, like how to build a Faraday cage. Are Faraday cages effective? Will a cell phone work in a Faraday cage? Actually, cell phones do work in Faraday cages these days. This is why light, which is also a form of electromagnetic radiation, can pass through the centimeter-sized holes. Let's see, good, interesting demo. What is this?
Have you ever noticed how there is very little or no range to your mobile phone inside a closed elevator? Your phone calls simply cannot connect.
Oh, okay.
Do you know why? The waves that give network coverage to our phone are electromagnetic in nature. These waves simply cannot enter a hollow metallic and magnetic conductor. So inside a metallic box, the intensity of electromagnetic radiation is zero. Even your radio won't be able to sync properly in the elevator. This is because the elevator acts as a Faraday cage. Let us try and make our own Faraday cage. All we need is a metallic lid that is magnetic and a metallic box that is closed from all the sides. Here, in front of us, we have a broken table fan. Notice how the radio does not receive any signal inside the box but sings beautifully outside. Isn't it amazing? A Faraday cage operates because an external electrical field causes the electrical charges within the cage's conducting material to be disturbed such that they cancel the field's effect in the cage's interior. You can find a real-life example of Faraday's cage right inside your kitchen. The metal shell in your microwave oven acts as a Faraday cage and prevents the microwaves inside the oven from leaking into the environment. So, dear friends, now you know why your phone simply does not work inside an elevator.
That was nice, short and nice. So we kind of got a sense of how wide of a field this is. The microwave, it was funny how they used just even a fan, the cover of a fan, and then the cell phone wouldn't. Now I want to try it at home. the fan, and put the phone there, see if it plays. Okay, so that all has to do with this. You see, the electric field is 0 and the voltage is 0 inside of the conducting. Now, if it's insulating,